Okay. Well, this is joint work with Monty Perry, now at the University of Warwick. Well, the title suggests, there was a book quite a while ago called "How to Gamble If You Must" by Dubbins and Savage, and I think that maybe we stole that title, of course, but I think that part of the feeling they might have had, I don't know for sure, but is that gambling is maybe considered a vice, and so you really shouldn't gamble, but if you're going to, here's how you should do it. Counting citations. I mean, maybe we shouldn't do it, but it's done, and people do it, and I don't think we're going to stop people from doing it, and so let's think about how we should do it if we're going to. So what's a citation index? They have various uses, and I don't want to overstate the extent to which decisions are critically dependent on a citation index. Okay, but there are all kinds of considerations that go into important decisions, and in some of those important decisions, citation counts are brought into the argument, and to the extent that we want to make arguments so as not to mislead and bring us to incorrect decisions, we want to make all of those aspects of our arguments as coherent as possible. So bringing in citations, we want to do that in a coherent way. So an index, what does it do? It maps non-negative integers into a real number. By the way, I meant this paper was published in 2016 in the AER, but and we present a theorem there. And what I've done for today's lecture is it's a group of theorists. I wanted to present you a somewhat more subtle theorem. So there's a difference in what I'm presenting today with the paper that if you look at the AER paper. So it maps a finite list of non-negative integers into a real number. Okay, good. What is this vector? It describes the record of a particular scholar. So here we have a record of n publications. So a paper for me is going to be a publication. And xi is the number of citations received by the ith publication in the list. Good. Now, of course, you're taking you have n papers. N could be quite large. A multidimensional object, mapping it into a single number, you're losing information. No question about it. So it seems inevitable that in any index function, any citation index that you write down, probably you're going to come up with examples here and there that seem to make the index look not so good. Okay? I mean, again, you're taking a multi-dimensional piece of information, mapping it into one dimension, you're losing stuff, no question. Nevertheless, we should want to try to make these indices as coherent as possible, and that's kind of the objective. What is the kind of information that you're losing? If you just look at the list of numbers and map that list of numbers into a number, what is the field? What is the journal? How many co-authors? How old is the paper? That'll affect how many citations you think it should have. How old is the scholar? And there are all kinds of things you might want that are important that you would want to add on, but I'm not going to. Most of that I'm not going to talk about. This is kind of a raw index, if you will. What are some examples of popular, commonly known indices? If you go to Google Scholar, you'll see the total citation index. That's just add up all your citations. That's the total citation count. Something called the I-10 index. What is that? That's just the number of your papers with at least 10 citations. And then there's the H index. What is that? It's the largest number, H, of papers of yours that each have at least H citations. Okay? And these are, you've probably heard of all of these, and as I said, you go to Google Scholar, you'll see those listed for any particular scholar who you Google. Now, of course, these indices are well-intentioned, and they have their purposes. I mean, they're designed to do something. So the total citation count, well, you could say it's sort of an unbiased count. The I-10 index, I guess it's supposed to count only significant papers, defined by having at least 10 citations. The H index, if you read Hirsch's original paper, it's designed to guard against a small number of very highly cited papers. Okay, so if you have 2 papers with 100 citations each, your H index is 2. You're equivalent to someone who has 2 papers with 2 citations each. Yes? So is that a good thing or a bad thing? Well, you can find examples. I just gave you an example. It doesn't sound so good, but you can find examples where it's kind of doing so. Okay. So we can talk about examples. And so, but when it comes down to it, a lot of these indices are sort of ad hoc. I mean, the rules of thumb. They are trying to express something intuitive, and that's usually described in words, and they do a good job. But you could think of other things. Yes, why not an I-20 index? Or what about an index that is the largest number G, such that the total citation count of the G most cited papers is at least G squared? That's an actual index to be, okay? It's called the G index. And it's meant as a correction to the H index for various things. So, but what we want is axioms, really, right? This is an area that kind of cries out for an axiomatic approach, and not to say, that this is the first attempt at axiomatizing citation. No, there's a whole literature on axiomatizing indices. Most of it, I should say, is axiomatizing existing indices. Okay, so indices that were invented, some ad hoc purpose, and then, what would be a set of axioms that generates that index? Okay, so in some sense, one wants to go, the other way around. Start from the axioms and see where it takes you. Okay, and this isn't even the first of that, of course. There are a few other examples. Let me just say that of the number of things that we won't take explicit account of, but this was something we will discuss. Differences across fields it's a contentious issue. I mean, if you've ever been in a department meeting where you're deciding on one scholar or another, and they're in different fields, and you're trying to think about how to compare someone in this field or that, that's when the discussion becomes interesting, right? It's hard. And so there is some general agreement if you look at the literature and citation indices, if you look at the bibliometric literature, so, that some kind of adjustment to indices is needed when comparing scholars across fields. Okay, and the sense is that in some fields the citation rates seem to be higher than in other fields, and so having a lot of citations in a field where people get a lot of citations, you should do some adjusting when comparing to fields where the number of citations, let's say the average number of citations, is lower. And in fact, the idea of rescaling the indices in some way to account for differences in average numbers of citations across field, that's a really it's an obvious idea, and it's an idea that you'll find in the literature over and over. And we'll talk about that. Let me go to the H index. H index is the H index is a really nifty idea. I mean, it's a very cute idea, and it's kind of popular. People understand kind of what it means on the face of it, and so it's used a lot. But I want to just point out that if one does think about comparing scholars across fields, and you adjust, and we'll talk about why you might want to adjust using the average number of citations, say rescaling by the average number of citations in a field, the H-index can give you trouble. In particular, it can reverse the ranking of scholars within a field. So let me give you an example, just a toy example, all right? So let's suppose you're a department, you've got 2 slots that you'd like to fill, and there are 3 candidates. There's an IO economist, 2 IO economists, and a macroeconomist. And, let's just say that it's a crazy idea, but you're going to make the decision based on the citation counts in some way, okay? Of course, you would never do this, but let's just talk about how that aspect would push your decision. So IO economist number 1 has 20 papers, each with 40 citations. So what's the largest number, H, such that this scholar has at least has H papers with at least H citations each, and that number is 20. She has 20 papers with at least 20 citations, but she does not have 21 papers that each have at least 21 citations. Yeah? So her H index is 20. The second IO economist has 25 papers, each with 15 citations, so her H index is 15. She does not have 16 papers that each have at least 16 citations, but 15, yes. Okay, let's say the macroeconomist's H index is 22. Let's just leave it at that. Now, people have done, looked at data, and Glenn Ellison is one of them, and we've looked at Glenn Ellison's data set, and he looks at citation rates, macroeconomists, IO economists, the various, and evidently macroeconomists received about 1.8 times as many citations as IO economists, okay? So if you're going to do this rescaling, then we should count every citation of an IO economist. If you want to compare to the macroeconomist, every citation of the IO economist should be 1.8. Should multiply it by 1.8 to match it up with a citation of the macroeconomist. So suppose we do that. Now, before the adjustment, the rescaling, who would we hire if we were? Well, we'd hire IO economist number 1 and the macroeconomist, 22 and 20, and third, coming in third is IO economist number 2. But we think, wait a second, we're comparing apples to oranges, we better rescale so we can compare these apples to apples, IO and macro. So let's multiply the citations of the IO economist by 1.8 so that we can compare those 2 economists with the macro. That's the point. We want to compare the IO with the macro guys. We already know how to compare the IO guys. That's not the issue. Okay, IO economist number 1 is better than IO economist number 2 according to the H index. So let's do now the multiplication. So if we multiply the 40 citations by 1.8 of IO economist number 1, we come to 72 citations in macro equivalent citations. And what does that do to the H index? Well, now she has at least 20 papers, each with 20 citations. So, that's it. She doesn't have 21 papers with 20. So nothing happens to her H index. It stays at 20. Second IO economist, we multiplied by 1.8, her 15 citations on each of her papers. So that stays at 20, 27. Okay, macro equivalent citations on each paper. So now she has 25 papers that each have at least 25 citations. So her H index jumps to 25. And so after doing the rescaling, so that we could compare the IO economist to the macro, not so that we weren't confused. We didn't think we were confused about the IO economist, but once we rescale, now we've reversed the order of the IO economist. The IO economist number 2 is better than IO economist number 1 in terms of the H index. Okay, so and I want to order I'm going to say that's a problem with the H index, not with the idea of rescaling, and we'll talk about that in a bit. Okay, so let me talk about axioms that we're going to think about. What time did we start at? What, 20 past? And so 20. Do we end at 20?
We end at 12:30.
12:30. Okay, 12:30. So what are the axioms? Again, what's a citation index? We're going to we're going to just, rank the, we're going to start with a list. You have n papers. The most cited paper has X1 citations, second most cited X2, etc. Let's rank them from highest to lowest, and then assign a number to that list. That's all that does is that just imposes symmetry. Okay, if I didn't do that, I would have to say that the index is symmetric. If you permute the order of the papers, it doesn't matter. But this just takes care of that. So what are the properties that we're going to impose? So the first one is a zero property, okay? You get credit for citations, not papers, okay? And so if you add a paper with 0 citations, nothing changes. We're going to wait to see if you get citations on that paper, and then we'll talk about how well that paper is how much that paper is helping you. So adding papers with 0 citations is not helpful. If you get more citations, that doesn't hurt you. Of course, that's good. Okay? No, of course not. If you get more citations on any existing papers, your index does not go down. So far, so good. Independence. A little tricky. What does this say? It says if you take two lists, ranking, say, one above the other. So suppose you're ranked above me in terms of your index, and now let's say we co-author a paper, for example. So that is where. So you add a paper, and we get the same. We each have a new paper, and we get the same number of citations on the new paper. That doesn't change our ranking. If you were above me before, you're above me now. Okay. Fourth property, what do we call it? We call it depth relevance. I mean, there's some idea that we shouldn't be trying to maximize the number of papers we write. Yes, that we should be trying to write good papers. Well, I don't know, good papers, more citations, let's say. So the idea is that it shouldn't always be the case. Always, the axiom is meant to be very weak. It shouldn't always be the case that whatever list you have and whatever paper in that list you choose that has more than 2 citations, and you take that paper, divided it into 2, and divide the citations between them in any way that's never worse for you. Okay? It shouldn't always be the case that you can take one paper, divide it into 2, divide the citations between them, and that doesn't hurt you. In other words, it shouldn't be the case that without loss you should just maximize the number of papers that have 1 citation each. Okay? So there should be some list and some occasion where if you were to divide this paper into 2 and split the citation, actually your index would go down. Okay? So it's meant to be a very weak imposition of the idea that we should want to write papers that have more citations rather than spread our citations as thinly as possible across as many publications as possible. Okay. Scale invariance. So what does this say? It says that if you take 2 lists, suppose again, take your list, suppose you're above me, okay, you're ranked above me, and if we just multiply your citations in all of your papers by 2, you get twice as many citations. I get twice as many citations. You're still above me. Okay, so just multiply your list by 2, multiply everything my list by 2. If you were above me before, you're above me now. That's what scale invariance says, and now we need to talk about this one a little bit. Okay, so notice, by the way, that if we were going to compare scholars from different fields, like I/O and macro, by rescaling the lists to take into account higher citation rates in, say, macro than I/O, and if you didn't want it to be the case that after you do that, you change the ranking of I/O economists, then you'd have to satisfy scale invariance to avoid that problem. Okay, that's. Let me give you another thought experiment that leads to scale invariance. Think about growth in a field. So there's just one field. Forget about comparing across field. There's just one field, okay? And we're going to think of the field as growing. And let me grow this field in a very simple way and extreme way in some sense. So there's one field, and let's just clone everybody in the field. So take everybody who's in the field, just give them a twin. Okay, that's all we're going to do. You give them a twin. So you've got twice as many scholars in this field. Each scholar has a twin who's written exactly the same papers, okay, and who's cited exactly the same other papers. I mean, that your papers are identical. So if I cited you, then my twin also cited you, okay? If you cited Peter, then your twin also cited Peter. Now, it seems natural, right, that I mean, my ranking, if I was, in the 75th percentile in this field, I should still be in the 75th percentile, me and my twin. Okay, so nobody's ranking here should have changed. In some sense, the indexes, the ranking between scholars of the indices shouldn't have changed if the index is doing a good job. But now, of course, everybody has twice as many citations. As I said, if you cited me before, so did your twin. So I have now twice as many citations. So actually, my list has doubled, and so everybody's lists have doubled. But in some sense, none of the quality of anything have changed. So that's a thought experiment that naturally leads to that you'd want scale invariance. If you think that fields are growing, and they're growing in this sort of way, even approximately. The index, if it's behaving well in growing fields, then it should satisfy scale invariance. Okay. There are two more properties I want to talk about. So I don't have room on the slide, so we'll move that up and we'll make some more room. And these are more technical. So let me now say that here's how this presentation today is more subtle than the AER paper. The AER paper, we just, let me say punted if you want. We just said, look, we're just going to think, if you think you have to rescale, for example, then you might, divide by the average number of citations. Then the index, you'd have to be prepared to at least looking at rational lists instead of integer lists. Well, if it's going to be all rational lists, let's just make the damn thing a function of real numbers. Let's just make the lists real numbers. And of course, it better be continuous. If it's not, that's just crazy not to have a continuous function. So let's just do that. Let's just suppose a citation list maps vectors of real numbers continuously into a real number. That's what we just started that way, not even saying it's an axiom. Okay, so that's it. And then given that's a definition of a citation index, what properties of that thing would you want? Okay, I'm not doing that here. I'm saying no. These lists operate on integers. If you want to multiply by average numbers of citations in a field, you can multiply by you can make it with the scale invariance. You can multiply by an integer and scale everything up. Okay. So it doesn't have to operate on rationals. It can still operate on integers, and you can rescale. So that's not an excuse for going to real numbers. So we have to do something. Continuity is going to have to come in, but we have to state it in terms of integers. So how to do that? The only way to do it is, so let me. And it's related to scale invariance, so this continuity property that I'm going to describe. So suppose that you have two lists, X and Y, and the index ranks X below Y. Okay? Let's suppose that you can, it doesn't so much matter, so let me not say it. And now let's talk again about the field is growing in this cloned way, if you like. So And so the field is growing. It's becoming twice as large, 3 times as large, etc., n times as large for some large n. Now, as that's happening, yes, our citations are growing just simply because the field is growing. We haven't even written any extra papers. The papers haven't gotten better. I mean, there's nothing happening. It's just we're getting more citations. And so, if we lived in a field that was this big versus this big, citations come more easily. There's kind of citation inflation is going on. Yes? So that, in this world, if I had gotten this many citations, this is my citation list in a smaller world. This is my citation list in this much larger world. And in this much larger world with citation inflation, the value of a single citation has gone down by a lot. I mean, compared to what it was before. And as you increase n, the value of a single citation is going down, 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 down. It's becoming just very easy. So, in fact, if this was worse than this, if this list was worse, x was worse than y in the small-sized field, in a very, very large-sized field, even if we added one more citation to each paper, well, this is a bold one, which has the same length as this list. That's minuscule in this large field. One citation with citation inflation. So we want this to be true for all sufficiently large n. Okay, so that's continuity. Okay. That's continuity. That's the rationale for this continuity. This assumption that I'm calling continuity. You might, since it's all integers, you might call it Archimedean. You might see. Let's call it continuity. Okay. The last property is another technical condition, and I'm just going to describe it here. The last property suppose you have three lists that are of the same length. Okay, so this absolute value means the number of papers in the list. So you have the same number of papers in each of these lists, and suppose that x is ranked less than y. And this z is going to be an increment. So now suppose a year goes by. So here's my list, here's your list. And next year we look and we see, oh, I've accrued z1, so this is a vector, z1, z2, z1 more citations on x on my first paper, z2 additional citations on my second paper, etc. So this is after a year, this is my new list. And suppose you also accrued exactly z1 more citations on your first paper, z2 on your second, okay? And when that happened, actually, it turns out I caught up to you and I overtook you. Suppose that's true. So suppose these two things are true. That at the beginning of the year, I was below you. We both accrued the same number of citations. Remember, we're ordering on our most cited paper and on our second most cited paper, etc. And now I've overtaken you. Then this says that if we continue to accrue citations at those same rates on our papers, you never overtake me again. I mean, I overtake you and I stay ahead of you now forever. So that okay. That's the last property. And maybe, in some sense, the least obvious, why is this natural? Okay? But we'll come back to it. But that's what it says, and that's how I would interpret what it's saying. Okay, that's it. Those are the properties. Question.
Just look at P1 and P6. So dimensional 1, if I increase zeros in the x, should I make more ones than the ones? How should I interpret this?
X can be 0, yeah. So what are you asking?
You put lots of zeros.
All zeros.
Lots of zeros in the x. Should I also put lots of ones in the x as well?
Here?
Yes.
This, yeah, I didn't say it, and I didn't even write it. I think I said it in words, but it's not on the slide. These are the same length. Okay? Just so I can add them without having to talk about what to do if they're not the same length. So they're the same length. So it should be on the slide, and it's not. I'm sorry. Does that answer your question? Okay, let me talk now about something that we call the Euclidean Index, and it will be for obvious reasons why we call it this. So the Euclidean Index assigns to any citation list its Euclidean length. Okay, so the iota subscript e will denote the Euclidean index, and it's just it. It's the Euclidean length of that vector. Let's say that two citation indices are equivalent if and only if they always agree on the ranking of any two citation lists. Okay, so if you take, for example, the Euclidean index, we could multiply it by 2, and those would be equivalent indices. Yes, they would rank any pair of indices the same way. And so, of course, in general, one of them is a positive monotone transformation of the other. Those indices will be equivalent. So here's the theorem. So if an index satisfies those 7 properties, the zero property, monotonicity, independence, depth relevance, scale invariance, continuity, and directional consistency, if and only if it's equivalent to the Euclidean index. Cheap advertisement here. Christian Zimmerman emailed Marty and I some time ago and said, "Hey, I put your index on our site. So if you want to do some computations with the Euclidean index now, you can do it." Okay. Back to more serious stuff. I think if there are two properties that one wants to have the most concern about here, say, I would say scale invariance and directional consistency. I think once one is comfortable with scale invariance, the continuity becomes more palatable. So I would say it's these two. Let's talk about scale invariance. I've given you there's this thought experiment of growth in a field, which I think is, it's kind of compelling. But let's talk about empirics. Let's talk about fields and how things go, in fact. And there's this really nifty paper by Radicchi, Fortunato, and Castellano, 2008, PNAS. And they look at citations across many fields, average distributions of citations across many fields, and they look to see what happens if you adjust lists by dividing by the average number of citations in the field. It's kind of what people talk about doing, but these guys actually go ahead and do it. So I've just this is taken out of their paper. So what do we have? They look at many fields, more than that's on this graph, this particular graph. In any case, this is a typical. What are the fields we have? Engineering, aerospace, biology, astronomy. The C0s here, that's the average number of citations in engineering, aerospace. And they're looking at a particular year, 1999, but we won't get bogged down in the details. Biology, 14.6, average number of citations per paper in that year, etc. And here we have the distribution of citations. So what's this? This is the number of citations received by papers. Okay, so there's 1 citation. Yes, there's 10. So it's a logarithmic scale here. And this is the fraction, the percentage of the field's papers with that many citations. So, a lot of papers are getting between 1 and 10 citations.
Fraction, presumably relevant percentage.
Yes, thank you. This is a fraction. Sorry. Yeah, sure. Exactly. This is the fraction of papers that receive C citations. And, the point of this picture is to show you that those are different across fields, those distributions, okay? They're not the same, then one can do, empirical tests, whatever, that they're not the same. Now, what did these guys do? They said, okay, let's take all of that data, and they have scholars, and they do, a lot of analysis, and they divide the citation lists by the average number of citations in the field, and they look at the distribution of citations after doing that. And that's what they get. So after dividing lists by the average number of citations in your field and looking at the distribution of citations, it essentially lines up almost perfectly. And, the reason, so this dashed line, I think they wanted to, for whatever reason, they're looking at log normal approximations, parameters that'll match the data. If they weren't concerned about log normality, this dotted part wouldn't be there. You just you ask yourself, are those distributions the same? And they'd be very much the same, not only here, but also over here. In any case, it's a remarkable, to me, it was they do some statistical analysis, which I'm not going to describe. But to me, it was just sort of almost impossible for this to be, true, just by dividing by the average number of citations in the field. Kind of matches up all of those distributions. It's amazing to me. But it might not be quite so amazing if we go back to the thought experiment. After all, if this is correct, that is that if fields are growing in some sort of a balanced way, as I described, and if it were true that fields aren't really different, people in different fields aren't different. You don't cite twice as much just because we're in I/O or macro versus I/O. It's just all it really is the different numbers of people in the field. That's all that's going on. If that's true, and the distributions across fields would be the same if the populations were the same, then of course you would expect that's exactly what would have to happen. If you divided by the average number of citations, the distributions would line up. Okay, so this seems, maybe it explains it, maybe it does, I don't know, but it's certainly consistent with the whole picture. And to the extent that one should do this sort of rescaling to correct for differences in fields, you definitely, scale invariance seems like an important property. Okay, so that's, the other one you might want to talk a little bit more about is directional consistency, right? This one over here, which I haven't, I told a story. The story seemed okay. I mean, it wasn't a crazy story, but not so really compelling, I wouldn't say. So really, the best I can do, talking about directional consistency, is to say, well, suppose we threw it out. Then what? And the answer is, if you get rid of directional consistency, then this is the theorem you get. You get a citation index satisfies all of the other axioms, except possibly directional consistency. If and only if it takes this form. So instead of sigma equals 2, which is the Euclidean index, you just get any sigma where sigma is bigger than 1. You get a whole class of indices that one-dimensional family of indices that satisfy the remaining properties. So we can see that the effect, the purpose of directional consistency is to pin down the value of sigma to 2. And of course, in order to present a practical index, it wouldn't be practical for us to say, here's an index, but I'm sorry, you've got to figure out your sigma. But what is the sigma doing? Of course, the sigma is playing a role, and the sigma is that there's a trade-off. Yes, quality, quantity, if you would like, and to the extent that sigma, take the limit, sigma going to 1. Then spreading your citations across papers doesn't hurt you, just doesn't matter how papers quantity versus quality. But sigma is bigger than 1, then you're starting to you're going to want to put citations, concentrate them in fewer papers. Okay. So why sigma equals 2? You know, if you're going to characterize a value of sigma, and by the way, the sigma has to be bigger than 1 for this depth relevance condition to be satisfied, so that's why sigma is bigger than 1. And if you're going to try to pin down a value of sigma that's bigger than 1 with an axiom that is at all, I think, simple, you know, your only hope is 2. I don't know. I mean, it's not a theorem, but I'm not sure how you would pin down sigma equals 3 or 7. So you can ask, well, look, how does it perform in practice, right? That's one thing you could ask. And again, Glenn Ellison has this data set. What do I have here? So what? And we just took Glenn's data. Okay. So there's a question, Kim Sao.
Phil, do you mean that if you further take away depth relevance, you will just extend the class to sigma smaller than 1?
Yes.
And that is still a one-dimensional class?
Yes. Thank you. Yeah. So Glenn has a data set. Let's see. Let's start with the NRC, the National Research Council in the U.S. They do a survey. They whose ultimate goal, and they do some statistical analysis. And in any case, they do a survey, and whose goal is to rank the departments in the U.S. So not just economics, other fields as well, but economics is one of them. And so the NRC produces a ranking of economics departments in the U.S. and I think Glenn looked at the top 50 economics departments in the U.S. and looked at the NRC's ranking. And then you can look at the economists who are in those departments at that time, and you can interpret the NRC's ranking, not only ranking departments, but ranking the economists who live in those departments, okay? So you could say that economist A is ranked higher than economist B if they're in different departments and the NRC ranked A's department above B's department. Okay, that's one way you could interpret. Now, economists within the same department, there's no ranking, okay? So one thing you could do, if you took that as some baseline, rough baseline of how, let's say the market, because the market places economists in departments and departments are ranked, and there's somehow think of the market as ranking scholars. Some baseline ranking of economists, you can compare that to any index. You come up with an index, you're going to rank economists. How does that compare to this, say, market-based ranking of the economists, okay, according to this? How would you test your index ranking of economists to the market one? It's an obvious thing to do is, you just, for any pair of economists, if you rank them the same way that the market did, give yourself a +1. If you misrank them, give yourself a -1. Do that for every pair. Add up the score over the total number of comparisons that you made, call that the score of your index. It turns out that that's a rank correlation test. Kendall, back in the, I don't know when, 50s, 30s, I forget now. It's an obvious thing to do. It's been done, and in any case, that's what we do. Of course, it's the natural thing to do. So here's a picture. We do this for the Euclidean index. We do this for the H index. Forget the blue line. Forget the sigma index for a second. So there's too much going on here. All I want you to look at first is here's the correlation coefficient, the score that you get with the Euclidean index when you do this exercise. The pluses and -1s divided by the total, you get 0.185. If you do it for the H index, you get a lower number, okay? So something near 0.16, okay? And one doesn't expect these numbers to be very high, and in general they're not. And they're not high here either, but there's a significant difference between the two. The other interesting thing that you can do, as I said, you can do this comparison for any index. So we have a whole family. Let's forget about this condition. We have a whole family of indices parametrized by sigma, And you can ask yourself, well, suppose we just wanted, let's let the data decide what the best sigma is. Okay? Which sigma would maximize this score against the market? And when you do the exercise, you can graph for every sigma the score. And here's the graph. Okay? And I mean, I promise, we did nothing to the data. We didn't do anything. The answer is sigma is 1.85. That's the maximum, okay? That's how to get the best fit with the data in this sense. You know, unrealistically close to 2. But there it is. Okay? And that's all I have. I think the next slide proves, right? So that's it. So that's it. That's. I'll just leave that as the last slide. You know, the other thing I can say is, for those of you who are probably asking yourselves the question, those 7 properties, they're independent. So if you take away any one, you can find an index that's different than the Euclidean index that satisfies all the rest. Okay, so all of the 7 properties are independent. And I should say, you know, this is a conference on, you know, dynamic mechanism design. No dynamics, no mechanism design. I'm sorry, but you know, it sort of begs the question. Suppose you were going. It's a nice research question. I don't know. I think there's been a little bit maybe. Olszewski and maybe a co-author at Northwestern have worked a little bit on this, but you could ask, you know, if you were going to design an index to have good incentive properties, or some, first of all, what do you maximum? What's the there are lots of questions. What's the objective function? And then, you know, what's the design, and how do you do it, and what might come out? And I have no clue whether that's an even really interesting problem or not, but it's one that comes to mind when thinking about the real focus of this conference. Anyway, thank you. That's it.